And I'm going to try to explain the idea to you first. And the volume of a cube is length times width times height. And like last week I talked about when you're trying to find volume, you can find volume by sliding area. So we can take the front face of this cube and push it back, and as that face slides back, we create the volume of that cube or this prism. It doesn't have to be a cube. But I could also slide different areas to get the same volume, and that's the idea here that we're going to use in a second. I could take the base and slide the base up and down to create the volume of this prism, or I could take the face on the side and slide it left to get the volume. Right? You guys see that? See how you can take different areas to get and slide the areas in a different direction to get the same volume. So now let's take a cylinder. The volume of a cylinder, what's the formula for the volume of a cylinder?
Pi r squared h.
That's right, pi r squared h. And what that's indicating is that you have pi r squared is the area of your circle, right? And that area slides height units. So pi r squared h is taking this circle area and sliding it. I could also take the top circle and slide that down. But the shell method takes the area, the volume of the cylinder, and computes it in an entirely new way. Right? And this is what's going to happen. Take a sheet of paper here. Okay. Here's what the shell method, what we're about to do, this is what the idea is. It takes a cylinder, like this sheet of paper, and instead of taking the base and sliding it this way, it's going to take the lateral area of this cylinder, and it's going to slide it. This is an area, and it's going to slide it inside of itself. So it's going to collapse inside of itself, like those Matryoshka dolls, where you've got like a doll inside of a doll, inside of a doll, inside of a doll. We're going to have a cylinder, slide it, and inside of there's a cylinder inside of that, slide it, another cylinder, slide it. And so as I slide the cylinder inwards, it fills all that space. Right? So you still have sliding area to create volume, but the area is all around, and that sliding area kind of collapses in on itself. Okay? So that's what the shell method is going to do, and that's what we're going to talk about. So this is the shell method. And I'll make up a problem that we'll start with. So let's set y equal x squared, x equal 1. So we're going to talk about a region bounded by y equals x squared, x equals 1, the x-axis, and we're going to rotate it around, rotated about the y-axis. Okay, that's the setup. So I'm going to draw the picture. Actually, let's make this x equal 2. Sorry, x equals 2. So this is a parabola. At x equals 2, we're there. So here's our region. This is our area. That's our bounded area. And I'm going to rotate that area about the y-axis, which then so when I rotate around, that's our mirror image area. So this area turns, so it rotates outside the smartboard, and then back inside the smartboard, and then out through the back of the smartboard, and comes back around. Got it? And here's how the shell method works then. Well, actually, first, let me draw the washer method to review. The washer method took a cross-section like that, and so you have these washers stacked on top of each other. Alright? So as these washers are sliding, are they sliding along the x-axis or the y-axis? The y-axis, because they're stacked on top of each other, right? And down here, your washers are really thick. Right? Up here, they're like really, really skinny. Okay, that's the washer method. The shell method, though, looks different. The shell method takes a cross-section vertically, apologize for my crappy drawings. But we've got this. This is my cylinder. And I'm going to take this cylinder, and it's going to expand and contract in on itself. And the area that we're counting is the area all the way around. So it's kind of like, if you take this region, it's like you've got this circular thing with a bowl on the inside, right? And as I take a cross section, it's like taking like a cookie cutter, and like punching it through. And that's the area that we're talking about, right? So this area is expanding. So, I could draw another cylinder. So over here we have this other cylinder, outside of it. Alright, so you've got cylinders inside of cylinders inside of cylinders. And that's how, so the sliding doesn't go left to right, top to bottom like we're used to. Alright, the sliding collapses in and it goes like, it contracts and expands. That's how the sliding works. Any questions? Okay, so, oops. I don't like having more than one cylinder on it because I think it just clutters things. So now we got to actually integrate this thing. So this volume is going to be the integral. Now, do we think this is going to be a dx or a dy integral? So how is this sliding? So as it slides, contracts in and out, it's moving along which axis? The x-axis. Right? In this cross-section that I drew, the thickness of that cross-section is dx. So it's going to be a dx integral. And we start at the origin, and so we're going to start at 0, and we're going to go to what? 2. A lot of people want to go from -2 to +2, but in the shell method, when you see the formula in a second, we'll take care of this left part of the formula. So you just want to go from 0 to 2, because only one cross-section is moving. Alright, also, we now have to figure out what the formula for the area is going to be. So we need the formula for the lateral area of the cylinder. So let me explain it here. Okay, so we've got the lateral area for the cylinder. Right, it's got a height. And then if I take scissors and I cut this cylinder out, it unfolds to become a rectangle. Correct? So the area of a rectangle is the height times this length. So the question is, what is that length? So Paul, what is this length?
That'd be 2 pi x times...
Let's just consider in terms of cylinder letters for right now. 2 pi
2 pi
r, right? Is this the circumference? Times height, exactly. Okay, so if I cut this and unfold it, this length across the sheet of paper is 2 pi r, because it was as part of the cylinder, times the height. So that's what our formula is going to be here. It's going to be 2 pi r h. And now obviously we have to figure out what r and h are in a second, but that's our formula. So this right here is the shell method. I've slowly tried to build it up and get you to understand the picture. But this is the shell method that we're going to do. And now we can figure out what all the values are. Okay? So, any questions here? Okay, so what we're going to do now is we have volume equals 2 pi, integrate from 0 to 2. This is a dx integral. So we need to write r and h in terms of the variable x. So, let's look at the cylinder. That's r, right? That's r. That's my radius. How can I express the radius in terms of x? Right. I just use x. Right? So given this, so like if we're at this point, that point has an x coordinate and a y coordinate. The y coordinate would be x squared, right? Y equals x squared. So this is like x comma x squared, but we just need the x coordinate. That's just x. So it's just going to be x. Alright, and now the height of this cylinder. What will this height be?
X squared.
I just gave it away, yeah. X squared. Alright, that height is y. Alright, but we can't put y in because it's a dx integral, so we're going to write y as x squared. There you go, that's it.